Buenas tardes, bienvenidos al seminario institucional del Instituto de Geofísica. Muchas gracias a los presentes aquí en el auditorio y también a la gente que está en las redes sociales y en Zoom viendo este seminario. Ahora me voy a pasar a inglés. Welcome everyone. Thank you for your presence here. Today we have a special seminar from a guest coming from Japan. Our guest is Dr. Hiromichi Nagao. Dr. Hiromichi Nagao is an associate professor at the Earthquake Research Institute of the University of Tokyo. He obtained his bachelor degree in the Faculty of Science in Kyoto University. He completed his master and PhD course in the Department of Geophysics from Kyoto University, obtaining a PhD degree in 2002. Afterwards, Dr. Nagao-san worked as a visiting scientist in the Japan Nuclear Cycle Development Institute, and then as a scientist in JAMSTEC, the Japanese Agency for Marine and Earth, for Japanese Agency for Science and Technology in Marine Science. Later on, he moved as a researcher and associate professor at the Institute of Statistical Mathematics. And then finally, he joined the Earthquake Research Institute at Tokyo University on 2013. Currently, he is also a faculty member of the Department of Mathematical Informatics in the Graduate School of Information Science and Technology of University. We're honored to have Hiromichi Nagao to give a seminar to our community here at UNAM. His talk is called AI Seismology in Japan. Very interesting topic. So please, Nagao-san, you're welcome to UNAM, and please go ahead.
Thank you. Okay, thank you, Ryman. So, can you hear me? Thank you. So, first of all, I'd like to say thank you very much to Doctors Rahman and Heramendo for their arrangements, not only this seminar, but also our visit to Caltech. Sorry, a visit to UNAM. So, we'll go to Caltech next week. So, uh, okay, so uh, uh, it's very honor to give a talk here UNAM. So in such a very nice auditorium. Okay, so my talk is AI seismology in Japan. Okay, so okay, this is the outline of my today's talk. So first I will introduce myself and our institute, and so the AI science projects. Okay, sorry, just okay. Then I'll talk about Synthesize, which is a national project related to AI seismology in Japan. So then I briefly introduce our colleagues' work, seismic wave picking from continuous waveforms based on deep learning. Okay, then I will introduce my study, so seismic event detection in historical records based on deep learning. Okay, okay, so Raymond so kindly introduced me. So my interest in information seismology, so such as application of cutting edge information science, including AI, to seismological issues. Okay, so now okay, this photo is this is a photo of what is this? This is a photo of our institute. Okay, our institute was established on November 13th, 1925. So this year is the 100th anniversary. Okay, so we have a ceremony last month, and so many people are attending at the ceremony. Okay, So we have more than 73 faculty members, so assistant professors, associate professors, and professors. Okay, and so overall, so we have more than 200 people in total, including postdocs and students and staff members. Okay, so our institute is a core institute of seismology and volcanology in Japan. Okay, so now this is a photo of my laboratory. So photo is taken. This photo was taken 2 years ago. So this is the end of the photo of the end year party of our laboratory. So this is the Japanese culture to have a party every year, every end years. Okay, so you can see our activities in our laboratory web. So you can see the QR code. Okay, so now let's start my talk. So okay, so now so as you know, so this is a big data era in seismology. Okay, so this map shows the distribution of seismic stations in Japan. In Japan, we have more than 2,000 seismic observatories. So inland and so ocean bottom or something and something like that. So such seismometers are observing so the ground motions. Uh, so in real time. So the all data were collected uh, and so to get so the concentrated in NIED, so which is a national institute of in Japan. So the data are available in real time. So okay, anyone can retrieve the data in real time. Okay, so uh, this graph indicates the number of earthquakes every years. Okay, so from 1997 to 2022. Okay, so you can see the number of earthquakes increased uh, here and suddenly rapidly increased here. Okay, so this is clear. So in 2011, so as you know, so we experienced a big earthquake uh, named so Tohoku earthquake on on March 11th. So uh, in this year, there were more than 300,000 earthquakes in this year. So the many aftershocks took place after the main shock. Okay, okay. So this is a natural phenomenon. This indicates the natural phenomenon. But so you can see the number of earthquakes increased around here. So this this indicates okay. So these seismic observatories uh, were installed. So after the Hyogo number earthquake, which took place in 1995. Okay, after that, Japanese government decided to establish such dense seismic arrays. And so, owing to this, so the uh, detection detection ability of earthquakes increased here. Okay, so this is not a natural phenomenon. So this is owing to the such this seismic arrays. Okay, so you can see the number of earthquakes drastically increased this year. So this is not also the natural phenomena. So the JMA, so Japan Meteorological Agency, okay, JMA, is working at the seismic phase peaking or something like that. Okay, so JMA adopts a new algorithm for phase picking. So the key technique is the particle filter method. Okay, so owing to this, the detection ability of the earthquake so drastically increased. So okay, so such as so the imagine so the uh, 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 so, a continuous earthquake so occurred in a short time. So before JMA using the particle filter, so such continuous such earthquake continuously occurs, so is determined as a one earthquake, single earthquake. But after that, after particle filter methods was introduced, so uh, 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 so many earthquakes can be resolved owing to this. Okay. Okay. Anyway, so this figure shows that the for seismic data analysis. Okay, so the number of data is important. It's obvious. So it's obvious, and so the improvement of the data analysis method is also important. Okay. Anyway, so cutting edge data analysis methods are required towards seismic big data era. Okay, probably this is the example of seismic of continuous records, seismic waveform records. Okay, if an earthquake takes place, you can see the P wave and S wave like this. Okay, so the JMA determines the arrival time, detects the P wave and S waves, and determines their arrival times in some way. So, mm, okay. Okay, this shows the conventional method to detect earthquakes. Probably you know STA over LTA methods. Okay, so this is a technique to detect the seismic phases in a continuous waveform. Okay, so this shows the original waveform. This is the result of application by STA to the original waveform. This is the result of application by LTA method. Okay, so the difference between them is in the time window, time length of the window. Okay, so STA applies a moving window having a time length of 1 second, and the LTA applies a moving time window having a time length of 300 seconds. Okay, and so this shows the ratio of STA and LTA, and so by doing this, we can easily detect the seismic events here and here. Okay, but so uh, from the statistical point of view, why this method works so well to detect to detect seismic events? Okay, but so in historically, so historically, GMA uses the SDLTA methods to detect seismic events. Okay, now after that, after detection of seismic events, GMA applied AR AIC method to determine the arrival times. Okay, AR means the autoregressive model. Okay, uh, autoregressive model, and AIC means the Akaike information criterion. Both of which, both are the statistics methods. Okay, I skipped the detailed explanation of this. So anyway, so AR models are moving AR models uh, uh, apply to the waveforms from left side and right side at the same time, and so the AIC is calculated so like this. Okay, so when the AIC achieved the minimum value, so this method data means that this time is the arrival time of P phase. Okay. So this anyway, so STLTA methods and ARAIC methods proposed for more than 40 years ago, but JMA is still using such conventional method to detect and determine the P and S wave arrivals. Okay. Now uh, uh, we have big data, seismic data here in Japan. So application of such conventional methods is getting harder. Okay, so now in 2018, so uh, Professor Zachary Ross at Caltech proposed a AI method to detect P and S phases in the continuous waveforms. So his method is named as generalized phase detection or GPD method. Okay, this is the this is the I think this is the first step of the AI. This is the dawn of the AI seismology. Okay, so um, uh, GPD method has a deep learning architecture shown like this. Okay, so if we input the such waveform to the deep learning model, this deep learning model outputs the probability of P and S phases and noise. P and S phases and noise. Okay, so this is the result of this is the output of this model. Uh, so it shows the red indicates the P phases and blue indicates the S phases and the black indicates the noise. Okay, so if we apply the if we input the continuous waveform like this to the model, so this automatically determines the P and S phase, P, S, and noise phases. Okay, so strictly speaking, this model outputs the probability of the existence of PS and noise phases. Okay. Okay. So Professor Zach Ross proposed the TPD method, so a number of deep learning models for the phase detection, phase picking are proposed. So the most famous one is the PhaseNet proposed by Zhu and Veroza at Stanford University in 2018. It has it has a unit structure like this. And so another famous model is the EQ transformer proposed by Musavi, also in Stanford University in 2020. Okay, so anyway, uh, okay. So anyway, so these three methods are the most famous phase picking methods based on deep learning. Okay, so at the so now so um, at the same time as the Jack Ross proposed the GPD method, in Japan, we launched a national project entitled such a long, it has a long name, entitled ISS Base in 2017. Okay, so the principal PI was the Professor Naoshi Hirata at the University of Tokyo. And so at the time, we developed many methods for seismic data analysis, including AI. Okay, so when we started this project, this indicates the number of papers related to the information AI seismology. So you can see the number of papers which is drastically was drastically increased in 2017 or 2018. Okay, so I usually say this year, 2017 is the first year for the AI seismology. Okay, so this project leads the information science in Japan. Okay, so after this project was completed in 2023, and after that, so I lead another national project related to information science, information seismology. Okay, so the current national project in related to information seismology in Japan is a study project sponsored by MEXT Japan. So MEXT is the governmental institute in Japan. So the MEXT leads MEXT is now leads the information science area in Japan. Okay, so what the in the study project, we have 5 research topics, and so one of them. So I'm a PI of one of the 5 research topics in study project. So you can see our outcomes in the website and newsletter. Okay, so the Dr. Harold is now postdoc employed in our project. Okay, so this is important information. So the study project will be completed next March. But so the next is now preparing for a success project, a new project. So which will launch next April. Okay. So our project will continue after for continue for more 5 years. Okay. So now, we are doing many research topics in our project, so I can't introduce all. So, I'll talk about a couple outcomes of in our project. Okay, just a moment. Okay, so we have developed a couple of phase picking methods using deep learning. So first one is developed by Dr. Tomoki Tokuda. Unfortunately, he's not here today. So he improved the GPD method Professor Zuckerberg proposed. So he combines a couple of GPD architectures. So like this. So, roughly speaking, his model has 3 architecture here, 3 parts here, main parts and subparts and subparts. Okay, so the main part of his model is consistent with the GPD model. Okay, so GPD model has an disadvantage. Uh, so this is an example certain waveform, and if we input this waveform to the original GPD method, so it outputs like this. So uh, in human eyes, so we can see the seismic event here and here and here. Okay, but so GPD method outputs more detects more events than expected. Okay, GPD method is too sensitive, so it detects as earthquake, but so it includes just noises. Okay, so GPD method easily determine the noise as earthquakes. Okay, this is the disadvantage of the original GPD method. Dr. Tomoki Tokuda adds this part and this part. So this part itself is the completely the same one as this, and this part is completely the same as this. But so this main part is applied to a size waveform of for 4 seconds. So it is the same. It is consistent GPD method, but this part apply the time window to the first half of uh, the time series, and this part applies that time window of 2 seconds in the second half of the original time series, and so his model combines the outputs, three outputs in some way, and so finally this outputs the probability of the existence of P and PS and noise phases. Okay, so this is a result of his proposed method. Okay, you can see the too sensitive feature in the GPD method was improved like this. So of course, so his method detects the seismic waveform in seismic events in the original waveform, but so such so sensitive results are depressed. So like this. Okay. So anyway, so he shows that his method is better performance than GPD original GPD method. Okay, so this method was already published in GJI in 2 years ago, and so uh, h- his code is available on GitHub. So if you are interested in, please visit this website. Okay, so next one is the sig phase. The next one is seg phase, so which is Dr. Shinya Kato proposed, and so he's now here, and so he'll talk about this uh, tomorrow noon here auditorium. Okay, so the advantage of his method, so he uh, he introduced the attention map function in his model, and his model seg phase outputs such so attention map shown here. So attention map indicates the place where the model focuses on. Okay, so red indicates the part that the model focuses on, and so for example, the model focuses on the P phase and S phase like this. Okay, this is a very good function of his model. Okay, so probably he will talk tomorrow. But so sig phase shows a better performance than the previous methods. So you can see that sig phase correctly uh, detects and determine the arrival times of P and S phases like this. And so this is the comparison between the seg phase and phase net results. So the red indicates the hypocenters determined based on the seg phase, and the blue dots indicates the hypocenters determined based on phase net. So the number of detections is much better in seg phase than phase net method. Okay. So you can see this graph indicates that so seg phase detects more earthquakes than the previous method. Okay. Probably you talk today. You talk this tomorrow. Okay. So please drop by noon here. Noon tomorrow here. Okay, so his method has been already published in a paper, journal, Time to Earth, Balance and Space this year, and so the code is also available on GitHub. Okay, so a couple of weeks ago, so Japanese newspaper introduced our this seg phase, introduced this our seg phase, okay, like this. So now this method is now getting popular, and so the purpose of our visit to UNAM this time is to introduce our AI techniques such as SegFace, and so please consider using our method to your data. Okay, so the next one is the face picking method for the dust data, so which is developed by Dr. Hermendo. So he gave a talk yesterday, and so so if you have questions, so ask him today. So we have a dust cable shown here. Okay, so this is a here is a Kamaishi, which is one of the cities in Tohoku area. Okay, so we have a dust cable like this. So the length of the cable is more than 100 kilometers. Okay, 100 more than 110 kilometers. Okay, so the gauge length is 100 meters, so which is like seismic stations located along the cable with the interval of 100 meters. Okay, the sampling rate is very high. We can have 800 hertz data is available. Okay, okay. So the number of channels is 50,000. So the span of spatial span is only 2 meters. Okay, so he developed now. So okay, uh, our final goal is to develop a deep learning, face-picking deep learning model for the dust data. But in order to develop such deep learning model, we need training data set. But we don't have training data set for dust data. Okay, so anyways, as a first step, we need to create training data. Okay, so Dr. Hermendo developed a method called SBR DAS, so which is detects the earthquake events from dust data based on template matching method and STLT and ARSC methods I talked uh, before today. Okay, so mm, the key point of his method is to use the sorry, is to use the I'm sure so. Okay. Mm. Okay. The key point his method is to using the SVR support vector regression method. Okay. So uh okay. So this is the his method consists of two stages. One is the earth detection stage, and the second stage the phase selection stage. Okay. So our method applies the template matching method to the original data, and the event detected like this. You can see the clear event here, and so our template matching outputs such events like this. And so the in the second stage, we apply the uh, uh, okay. So okay. Okay. We apply the STFT method and ARAC method to determine the arrival times, but you can see the determination of arrival time is incompleted. Okay, by applying SVR method to this, and we can get clear uh, certain phases like this. Okay, so S- So okay, So I don't talk the details why the SVR methods works well like this. So anyway, so now we almost completed to create training data sets by our method. Okay, so after that, uh, Dr. Hermendo is developing a deep learning model for face picking. So he adopts a BERT model, so which is proposed by Google in probably 2018. Okay, this model is for a natural language processing model, so capable of deep contextual understanding by processing sentences from both directions. Okay, so he improved the BERT model, and so sorry, he improved this BERT model to be applicable to DAS data. And so, okay, he showed the initial result yesterday talk, and so our model work. He showed our worked worked well for the dust for the phase picking in the dust data. Okay, so he gave talk yesterday, but ask him so if we have any questions on this. Okay, now let's move to my work. Okay, now so I'm very interested in the AI application to the historical records obtained by old mechanical seismograms. Okay, so the target is the deep low frequency tremors recorded in historical paper record. Okay, so probably use over 2002 discovered slow earthquakes. So owing to the such dense seismic using such dense seismic observatories network. Okay, so now our target is a low frequency tremors, so which is one of the slow earthquake events. Okay, this is an example of the low frequency tremors recorded in one station. Okay, so uh, okay, this is the sorry, 1 hour data. This includes the 1 hour data, and so one trace indicates the 1 minute, 60 seconds. Okay, so you can see the noise. You can see the amplitude. This waveform amplified, somewhat amplified. Okay, so in the old before establishing such dense seismic arrays, so the seismologists at the time didn't notice this is a seismic event. This is they thought this is just noise. Noise was amplified. Okay, but so Professor Obara noticed this is a seismic event by uh, comparing the uh, comparing the such uh, waveforms comparing the nearby seismic high-net observatories. Okay, so after that, so he developed he and so many other seismologists uh, started to create the tremor catalogs. Uh, Tremor catalogs, so using high-net observatories, but so such tremors can be detected by using the HiNet data. So we can create only 20 years, a little bit more tremor cutoffs for recent 20 years or a little bit more. Okay, so uh, such slow earthquakes frequency tremors are uh, estimated to relate with the plate boundary massive earthquakes. So, but so Nankai Trough earthquakes took place is well known to take place with a period of 100 or 200 years. So, in order to know the relation between the such massive plate boundary earthquakes and slow earthquakes, we need more tremor catalogs having more years. But we can, now uh, uh, tremor catalog of 20 years only available. So we so so but we have seismic records more than before establishing the high such seismic depth observatories. So the so 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 about 4 or 5 years ago, Professor Obara asked me to develop a deep learning model to detect the seismic low frequency tremor in a historical paper records. Okay. Oh, so I saw many old mechanical seismometers here in Yunnan. So our institute also uh, keep such mechanical seismogram. Okay, so probably old mechanical seismograph has a big drum, and so the s- uh, the technician at the time uh, put on a big paper on the drum, and so uh, the pens directly record the seismic waveform like this. So this is the example of a paper record that about 60 years ago. So this paper contains data of 1 day. Okay, so this is the enlargement of this part. When an earthquake takes place, you can see the successive phases, and so probably so you can see the black belt here and here. So the seismologist at the time probably didn't notice this is a seismic event, but the seismologist at this time, uh, when a seismologist this record, uh, uh, see this record, sorry, this this may be the low frequency tremors. That took place 50 or 60 years ago. Okay, so the purpose of our study is to develop such deep learning models that can detect such low frequency tremors in a paper record. Okay, so our institute had 10 or 11 seismic observatories in Wakayama Prefecture in Western Japan, uh, which indicates in the uh, purple stars. Okay, so this indicates the hypocenters of low frequency tremors that took place in recent 20 years. So uh, luckily, so the old our seismic stations were uh, located at the zone of the low frequency tremors. Okay, so we have a number of historical seismographs like this, more than almost uh, almost 20,000 paper records in our institute. So then we scanned a part of the seismograms of this, so we converted to the images or converted from the paper records. Okay, so of course it took massive budget. Sorry. Okay, this is the example of the paper record. So one paper record contains the data of 1 day. So 1 day, and so the horizontal indicates the 2 point. 150 seconds. Okay, which is a speed of the rotating drum. Okay, so the rotating drum rotates with a period of 150 seconds at the time. Okay, so first we scan such paper records into an image. Okay, this is another example. So we can so uh we can notice the these are the tremor low frequency tremor events at the time. Okay, so seismologists at the time probably didn't notice these are the seismic events. Okay. Okay, so this is a strategy to develop deep learning model. We adopt a resonant architecture for the model. So after we constructing the model, so we trained a model by using training data set. So first, we created artificial images by referring to the actual images. Okay, this is the actual image of the paper record. This is a imitation I created using my PC. Okay, so I inserted sometimes earthquake events like this and tremor events like this. Okay, okay, so I created a number of such artificial images, and uh, our model is pre-trained by using such artificial images. Then we created another training data set based on modern HiNet data. Okay, so in recent 20 years, uh, we know where and when frequent low frequency tremor took place. So we have uh, tremor catalog developed by Professor Obara. So by referring to this, we created many images based on HiNet data, which include tremor, and so didn't include tremors. Okay, we created both images, including tremors and not including tremors. Okay, so then we fine tune. I've fine tuned our model by using such training data sets. Then finally, we applied the trained our model to the actual data set, and we tried to detect the low frequency tremors that took place 50 or 60 years ago. Okay. Oh, okay. So this is a brief explanation how we trained our model. Okay. By using the artificial images, so we trained our model to achieve the accuracy of 100%. Then we use the such images, so created from HiNet data. So we created 50,000 images, and we achieved the accuracy of more than 98%. Okay. Okay. So this is the example of applications of model to actual historical seismograph. So this is a successful example, and so we uh, we install the also the attention. Our model can also the output such attention map, uh, which shows the where the our model focuses on in the input images. Okay, so our model can our model so often successfully detects the low frequency tremor at the time like this. And so we install the grad GAN method to output the attention map, and the attention map clearly shows the oh here's the tremors in the original image. Okay, so but actually there are some unsuccessful cases. Okay, so you can see that this result is clearly bad. So we published a paper 2 years ago related to our work related to this, but at that time when we published the uh, well, when we published the paper, we didn't know the cause why we didn't know cause the we didn't know the why sorry we didn't know the cause why there are successful and unsuccessful cases. So the first author was my student. So he noticed that so if the uh, if the pen thickness if the pen was thin, so our model successful to detect tremors, but the pen in the original record was thick. Our model was unsuccessful for detection. Okay, so but I didn't we didn't know still so why there's cases the pen was thick and pen was thin and pen was thick. Okay, so uh, our staff found a paper recently, found a document recently. Uh, sorry, recently. Okay. So so the pen this thickness was correct. Is normal. Okay, so the thick pen was abnormal. Okay, the document said the pen nibs gather dust so for a long time, but at the time, so the technicians clean the pen nibs so not so often. So pen thickness so changes over a long time. So we didn't know that. We didn't know that we didn't know there are such cases in the original paper records. So after we publish a paper, we try to create more training data sets that include the pen thickness, but the pen is thick. Okay. Okay. Original. Just a moment. Sorry, I'm confused. So, okay, when we created the training data set, we used the pen, we used a thin pen, okay? So our model can detect only uh, uh, our model can detect tremors only in only for the original data using a thin pen, okay? So now we are trying to create a training data set using a thin, also the thick pens. Okay, now probably we can improve our methods in a couple of years. Okay, okay. So our work another new Japanese newspaper found our paper and they kindly introduced our work in a newspaper 2 years ago, and so NHK, which is a national TV broadcasting, also introduced our work in a TV program. Okay, okay. So now we are doing another. We are now trying another historical paper record. So it's a hard work. So Dr. Shinya Kato is now working on this study. So we have another kind of historical paper records, so which is smoked seismograms. Okay, so we have a room to we have a special room for the smoked seismograms. So we have we have microfilms stored in the microfilms in which so there are many photos of such smoke seismographs. So uh, we converted such smoke uh, seismogram photos to the images. So we converted more than 50,000 smoke seismogram photos to the images. Okay, so like this. So, you can see that it seems to very hard to detect such seismic events from such images. Okay, so now this is a very this is an example of smoke seismogram uh, uh, observed in Mount Azuma, which is in Fukushima Prefecture. Okay, so you can see this is a very clean. This is a very clear smoke seismogram. And you can see the seismic. Okay, okay. You can see the earthquake events here and here, and so you can also see the tremor events like this. So our purpose is to develop deep learning models to detect such earthquake or tremor events from a smoke seismogram. Okay, so this shows a sketch of the our deep learning model architecture. So we adopted a, detection a detection transformer method uh, support, suggested by Carrion et al. 2020. So it so this method can detect and so detect the events and classify the events. Okay, so in concretely, so our model detects the events in a smoke seismogram, and it classifies into earthquakes and tremors and noises. Okay, so no, okay, and so okay, so now let me show the result here. So our models is now being developed. So this is the application example for the test data. So this is the artificial images. Okay, so this is the level data. So we know the where the tremor is, and so we know this is the tremor and where tremor is. So our model outputs the location of tremors in the input image, and it classifies this event in the tremor with the probability of these values. Okay. Okay. So this shows that our model works well because so our model detects uh, tremor events, and so it classifies in that it as tremor correctly. Okay. And this is another example. So when the input image contains the earthquake events here and here, our model also works well. So our model found the uh, 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 found the earthquake events correctly, and it classifies these are the tremors with probability these values correctly. Okay. Okay, let me skip. So this is okay. So there's an unsuccessful cases. So now we are now train. We are now uh, doing training of a model continuously, and so we expected to complete a model in a few years. Okay. Okay. So uh, anyway, so we'll Now, let me conclude my talk. The the key point I'd like to say that so in Japan there is a big national project related to AI seismology, and so the government evaluated our project is successful. So our project is now completed in next March, but so our Japanese government is preparing a success project to launch in next April. So it will continue for more 5 years. Okay. Okay, so now, as I said, the purpose we visit UNAM this time is to collaborate with you. So, in particular, uh, so so I'd like you to use our AI techniques to your data. Okay, so uh, anyway, so we'd like to collaborate with you. So starting from this year. Okay, so sorry for my poor English. So uh, I hope you understand our activities and so what we are doing now and what we will do in future. Okay. So so let me conclude my presentations, and I'd like to say thank you very much to my current laboratory members and alumni. Okay. So thank you for attention, and so I hope a good collaboration with you. Okay. Thank you so much.
Okay, thank you so much, Nagao-san. So now we have a few minutes for a couple of questions. Anybody in here in the auditorium, any questions?
Thank you very much for your talk. Um, well, we have, I have maybe too many questions for you, but maybe I only wish to ask one or two. Do you think that the procedures that you have right now would be able to identify, for example, earthquakes using smoked papers, but that they are very old and in some cases very damaged,
Yeah.
and also that maybe the instruments were not, the papers are not so well cared. So do you think it's possible to do that?
Good question. So I show only the good case. It's the cleanest data. So clearest data. So as I show, I just show. So yeah, this is the worst case. Might be so. Professional seismologists can detect seismic events by eyes like this. But so now we are trying uh, the best cases like this. Okay, so uh, so uh, I showed this example. So this is not a smoked seismogram. So this seismogram was drawn by pens, using pens. So such seismometers were used 50 or 60 years ago. So it's like a revolution in a seismograph. So this seismograph is used after smoked seismograph is used. Okay, so this is a very clear. This such so paper records using pens are very clear data, but as you said, so smoke seismograph is not so. For example, so okay, probably it's very hard to see. So this smoke seismograph was obtained more than 100 years ago. So it's it looks much different from like this. Okay, so you can see the very you can see high frequency components in the events in this case because this record is obtained on just only 30 years ago. So this is relatively new, but in all times probably the characteristic also characteristic or features of seismographs are much different between these. So if we see if we see such records obtained all times, might be uh, high frequency component of the events are not recorded. Okay, so uh, 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 we believe so. We believe of course, earthquake events. So in the relatively new records obtained 30 years ago, it includes tremor events. It records tremor events, but okay, okay. So in such old, very old records, we couldn't find any tremor events, just earthquakes. Probably, so the high frequency component uh, could not be could not be recorded in all seismographs. So we believe our uh, our study will be successful in the relatively new smoke seismographs. But as you said, so it's very hard to apply our method to such old records. Okay. Thank you for your question.
Okay. Could you put the slide with the thickness, with the pen thickness, please?
Oh.
This may be like a very naive
Sorry.
question, maybe, but oh,
Maybe this.
yes, that one. Thank you. So, how hard would it be to use like a pre-processing step where you use segmentation in the image? So that way you can have like the line and then reduce the thickness and keep the same architecture.
Good question. So actually, I skipped the explanation for pre-processing. Okay. So actually, this image has a size of more than 60 megabytes. So it's very hard to input directly to our model. Okay. So we divide it into 5 portions, vertical portion like this. Okay, so crossing the time courses. Okay, so this idea. So Professor Obara suggested this idea. So the target. So target tremor events. Our target tremor events is uh, uh, our target is the tremors having duration more than 1 hour. Okay, so as I said, so horizontal axis means the time length of 150 seconds. So the tremors having more than 1 hour are shown like a black belt. Okay, so if we divide into 5 portions, and okay, we input each portion to our model. Okay, so our model, okay, you can see our model outputs the probability of tremor existence. So this indicates that our model. Also, this indicates this portion contains a tremor event with a probability of 100%. Okay, 100%, 100. This is a good case. But sometimes our model fails to detect tremors, and in such cases the probability is lower. For example, 30% or 40%, like that. But so if our model missed to detect tremors, only one or two portions, the result of other portions covered such misdetection. Okay, so this is our pre-processing. My answer is
But could you use like a segmentation technique to identify like those seismograms that have like a thick pen, and then automatically reduce the thickness of the pen and keep the same architecture, and then you get rid of this problem, ideally, obviously.
okay. Thank you.
Gerardo, ¿me ayudas a pasar el micrófono?
Professor Nagao, thank you very much for your talk here. Well, my question is related with the previous one about you didn't talk about the pre-processing that you use to improve images. I know that there is a lot of with AI. There has been a lot of effort to recover like old pictures, old movies, to improve them, to remove noise. So I would like to know how much effort have you put on the pre-processing of the images just before working on trying to detect earthquakes, tremors? Thank you.
Sorry. So let me confirm your question. So, are you asking on the
I'm asking, for example, how much, once you have a picture of your records of on paper or with these smoked seismograms, do you apply some kind of pre-processing of the images to improve the contrast, to remove noise?
I see.
Uh,
Yeah. So,
yes, thank you.
thank you for a good question. So, we also developed. I skipped the pre-processing process for the smoke seismogram. So, actually, so, let me so, okay, okay. So, you can see that. Um, you can see. So, this is the original smoke seismogram. But so, so when so when the technicians took photo of this, and so took photos, so took photo of this, and so the recorded in microfilms, so they added such notes for each size small size one. So now, so we just a moment. So what we need is only this. So we need to erase. We need to remove this. So the uh, such memorandum and so surrounding areas. Okay. So we developed to extract the original seismogram from images. So we developed such program for person program. So when the technician took photos, so the probably the camera tilts some just not saying in English. So the camera took photo the technician took sorry, the camera tilted, somewhat tilted. So so we we developed a program to rotate to rotate the photos to the original position. Okay, and so actually, so we try to develop a processing program to clean this. So I'm sure I don't know I'm not a professional technician. So such if so you can see the waveforms behind the clouds, behind such clouds. So such this so I'm sure. So after recording after complete after the smoke side smoke after the after the recording, so I'm sure hats in English. So in Japan we say so at, I'm sure so sorry. So anyway, such so large scale noises have a long wavelength, such so cloudy noises have a long wavelength. So uh, if we apply spatial FFT to the original data, so such so cloudy noises can be removed, but not so clear. The result was not so clear. But so uh, after that, after such processing, so we think so might be uh, this data might be available. Okay, so I'm sure so my answer is correctly. I can answer your question correctly. It's about the effort that done to improve the images. Yeah, yeah. As you say, so pre-processing is very, very important in this case. Thank you for your question.
Thank you. Congratulations. Your talk was very interesting.
Thank you.
And I want to know what about the successful cases? You have some good results regarding, you know, uh, improve the statistics of what is you mentioned at the beginning that you want to get a more clear idea of the statistics of the different types of earthquakes, slow earthquakes. That's what Professor Obara was asking to you. Uh, because, yeah, and you mentioned the cases, the problems, the processing is really very hard, and we have to congratulate you for this effort. But the idea will be what what case of successful examples, what is the things you learned? You improve the statistics of the micro tremors, of the tremors, or maybe the slow earthquakes. What were the results or preliminary results of your quest?
So, probably so. I don't figure out yet. So, question.
The question, maybe you can phrase it.
Sorry. Detections. Have you been able to determine, learn something new about seismicity or slow earthquakes in Japan?
Okay. So if we uh, if we succeeded in tremor catalogs for a long time.
Yeah, now that you have more detections on tremors, earthquakes, have you learned something
¿Y
new
para qué le pregunto
in
después?
seismicity in Japan?
So, just one.
ですけど、これはね、地上学習の、方法、
En los
世
casos
界なんですけど、この結果は、
que aprendió
世
de
界
los
ですね。
casos,
これは、何を、勉強しました。これはね、移動は、検出ですね。
はい。
その検出は、 他のデータに、
Sus tablas japonesas, ¿no?
同じは世界ですか、新しい微動の
So,
他の
so maybe we can. Sorry.
Okay, let's discuss later. Okay.
Yeah, we can.
Sorry for that.
Talk a little more between both of you. I think we're running out of time. If there's a few other questions online, I'm gonna pass you the online questions so we can discuss them and maybe we can answer them later. If people here has any other additional questions, please I encourage you to approach Nagao-san personally and you can have a small chat asking some of the questions. He's gonna be here today and tomorrow. So there's a chance for you to talk with him a little bit more. So we appreciate your talk, Nagao-san. Thank you so much for this very interesting talk. Hopefully we can start collaborations with ERI, with Nagao-san's lab here in UNAM. So the opportunities is here for UNAM people to start using some of the tools they've been developing. And thank you so much for coming to UNAM. Thank you for your presentation and hopefully we'll meet again very soon.
Thank you.